because there are so many of these different Catalan objects, there's so many rabbit holes to go down. Like,
Hmm.
and this is true for a lot of math research, but like particularly with this problem, there's just like so many different directions that you could theoretically go down. And it's like, okay, I stumbled upon something that was really cool, but it's like someone already went down that way.
But it's pretty cool. So what you're doing specifically, no one else has come up with a solution for. Is
Not
that
this question, correct? Yeah.
Hey, we're Beyond Me, the show where mechanical engineering students go beyond ME, and where the things we talk about are beyond us. We like thinking broader, we like thinking deeper. I'm Ben, here with my co-hosts Finian
Hey, how's it going?
and Liam.
what's up?
Finian, who are we talking to today?
Today, we're talking with my childhood best friend, Theo Lurie. We're going to be talking about discrete math research, Catalan numbers, and n-gons.
That sounds great. Sounds like a lot of math. Liam, how do you feel about math?
Math is tight.
Math is tight? Let's get into it.
All right, Theo, thanks so much for joining us. Why don't you give a little background about who you are, what you do?
Sure. My name is Theo. I'm a rising junior, I guess, now at Swarthmore College, which is in the Philly area. I'm a mathematics major and a linguistics minor, and I'm currently employed by my school, working for the mathematics department in some discrete math flavored research for the summer months. It's kind of the gist of that.
I didn't know research could be flavored. I'm intrigued
Yeah.
already.
Oh, the I don't know. That's the term that I think has been introduced to me pretty frequently now, is to refer
Mhm.
to the continuous flavor and the discrete flavor of math.
So,
So,
what's the difference?
what is... Yeah, I was going to ask the same thing.
Vinny and I we're on the same wavelength here.
Yeah, yeah. Well, I think that how I've come to kind of like understand some of the delineations of the different mathematical fields is there are like definitely tiers, and I think one of the highest, like, just to split it into two categories, is like discrete math and continuous math. And continuous math, I mean, quintessentially is going to be like your calculus based math. So yeah, calculus, real analysis, which is basically the theory behind calculus. And then discrete math are things like combinatorics, number theory, stuff that works with integers, whole numbers, rationals. You're dealing less with infinity in something like discrete math. Calculus is very like infinitesimal. And so is real analysis in those fields.
You mentioned tiers earlier. Is that in like complexity, or is that like different levels? Like you go from like calculus 1 to calculus 2. I know that's not going to be a different tier, but it's a different in difficulty along with like extra material and more concepts. Is it tiers as in like the math just becomes more difficult because you're having to do more transformations through equations? Or is it tiers in the sense of like it's the difference between calculus and linear algebra?
I would say that maybe tier was not quite the best word, but man, the way that I think about it is like you have your big like math umbrella, and you're trying to like divide it up into like what the different subsets are, and it's definitely not this simple, but because so many of them interact with each other. But if I were to then break that big like mathematics umbrella into two smaller categories, the first step would be continuous and discrete.
Okay.
Mainly
So
speaking in a strictly pure math standpoint.
Which one are you studying?
I definitely fall into the discrete category for the majority of what I'm working on and what I tend to be interested in.
I'm curious how you actually study math at this point. Like, I feel like math is pretty well discovered. Like, what does your day to day in this job
Um,
actually
This
look
is going to
like?
be one of my questions. It's like we
Yeah.
have a
yeah.
math. What more math is there?
So yeah, that's honestly that's the question that I get like kind of immediately every time when someone was like, okay, like, well, what are you doing this summer? And I'm researching math, and then it's always like, okay, what does math research actually look like? And for a while, I was just kind of like, well, I don't know, I haven't done it yet, so I'll figure it out. Um, but the what my day to day looks like right now is that I go to campus and I sit in a room with a chalkboard and I think and I draw pictures of shapes. And that's kind of all that's a lot of it. But in a more like general sense, that's not just like specifically what I'm doing right now. I think that the best way that I would describe what math research looks like is that there is quite a bit of like there's always new math. I think that like what I've heard a lot from professors is that today's pure math is tomorrow's applied math. So like a field like topology is not particularly old. It's a relatively new field of math, um, but was initially studied out of a pure like curiosity standpoint, like something like the pure maths would be considered, but now is actually being used in things like mapping like protein structures in like biochemistry is the one that comes to mind. Topology is a hard field to describe, but it has a lot to do with like classifying shapes. Um, and so the stuff that I'm doing right now is not at all related to that, but um, there are like plenty of questions that people don't know the answers to about certain things. And also,
Very
I mean,
descriptive.
I know that's quite vague. I think it's hard. It would be hard to get into without like using all of the vocabulary. Um, and I'm trying to speak a little bit more universally, but I think that like there a lot of the like math research and like the breakthroughs in math that happen now tend to be as like also um, things that bring like fields together in interesting ways that you wouldn't have expected, as opposed to like generating entirely new fields of math.
Mm, mm.
A lot of the like Fields medalists, which is like the math equivalent of the Nobel Prize. These people have like written proofs or made connections between fields that use these like kind of disparate corners of math um, in interesting ways. And then there also is a component to math research that I think is what tends to feel more researchy, which is that um, it's a lot of like collecting data and finding patterns. Um, so when I am like sitting down and trying to figure something out, I don't go right into a proof. In fact, I haven't really done many formal proofs at all in my research yet. It's a lot of I'm generating a lot of data and trying to see like identify certain like mathematical structures that I'm familiar with. And that's kind of how math research or just math in general has worked for a while. Even like someone like Newton, who like, I don't know if you're familiar with like Newton's method, but it is a particular way to find the zeros of polynomials. And it's an iterative process, so it requires doing multiple calculations. And nowadays, it's something very easy to do, like on a spreadsheet, that you can just generate a billion like data points in very quickly. But Newton was like doing all of those calculations by hand. So the research now looks similar in that it's still generating a bunch of data, but it can be done a lot quicker and you can do more complicated things.
Yeah, I
Yeah,
remember visiting you, and you were talking a lot about like going to work and then working on spreadsheets. And I was very interested, like not interested, but I found it fascinating because I always imagined going and doing math research as like, all right, a bunch of people in tweed jackets go into a room with a blackboard and then haggle over what's the correct like sign in front of this variable.
Well, that's what I kind of want to know. What is your actually? Can you get more specific on what you're actually doing right now? Because I'm just very, unlike Finian, I
Yeah.
am actually interested.
No, for sure. I definitely can. So, and this is like, it might be a little bit dense. But so what I'm currently working on are these things called Catalan objects. And Catalan objects is a term for like an interpretation of this very famous sequence of numbers called the Catalan numbers, which are recursively generated. A recursively generated like sequence that you're probably familiar with is like the Fibonacci.
Mhm.
And these are related to the Fibonacci numbers, but they're generated in a different way. And yeah, so they're generated recursively, which yeah, means that they are dependent on the entries, the indices before them. And they are like particularly dense in terms of study because they have so many interpretations, and all of these different interpretations are the Catalan objects. And particularly the two that I'm working on right now are the ways to arrange strings of parentheses in like sets of multiplications. So if you have like three elements that you're multiplying in only pairs, there are two ways to legally arrange your parentheses around those three objects that will like two unique ways. It's basically just recursively applying associativity, the property of associativity to these sets of numbers, or not necessarily numbers, but just elements of a given set. And I am, and those number of ways correspond to Catalan numbers. So the Catalan the starting sequence is 1, 1, 2, 5, 14, 42, 132. Keeps going. I can describe the recursion, but it's a little bit dense. But these sequences of parentheses for if you have n elements, you will be able to create you'll be able to generate a number of legal strings of parentheses equal to the n minus 1th Catalan number. And the related Catalan object that I'm drawing these connections to is something that seems particularly unrelated, but is actually very closely intertwined, and it is the number of ways to triangulate an n-gon. So an n-gon is any like polygon that is uniform. So like square, triangle, pentagon, hexagon, etc. Always obtuse angles. And triangulating these is it kind of self-explanatory. It is what it sounds like. It's like drawing chords from vertices to vertices inside non-crossing chords that divide the shape into triangles. And the number of ways to do that for a shape with n vertices is the n minus 2th Catalan number. So there is a bijection between the ways to arrange these parentheses around elements and the ways to triangulate different shapes.
Wait, can I just real quick? So with that, like if you had a square and you put a diagonal line, that makes two triangles, which is n minus 2 four sides for the square. Is that what you mean, or four vertices for the square?
So yeah,
Is that the correct interpretation?
What I mean is that, so if you think about that, you have that square and you can draw the diagonal from like the top right to the bottom left. So that's one way to triangulate a square. You can also draw the diagonal from I forget which one I said, but the other diagonal.
Yeah, the top left to bottom right.
Yeah, exactly.
That's what it describes.
There are two ways, yeah. And for a pentagon, there are 5 ways to uniquely triangulate that pentagon.
So it's not just the number of sides, obviously, but it's somehow related to it's the number of ways to triangulate an n-gon is, so whatever n is, it's you take n minus 2, and that number in the sequence of the, what's it called again?
The Catalan numbers.
The catalan, that is the number of ways to triangulate that n-gon.
Yes, exactly.
Okay, wait, and then, so you were also talking about taking strings of parentheses. I sort of got lost with how many parentheses do you have, and how many numbers are there?
Mm-hmm. So, yeah, it's I definitely would be...
That's like the whole thing with math.
In hindsight, it could have probably been better if I had like been on campus and could have like a blackboard or something behind me.
Finian will do a Manum representation of this and put it on the video.
I will not.
Yay, Finian.
But so let me try and think of a little bit of a better way to describe this. But like, so if you have, okay, so if we were thinking about the squares, so we can talk about, say you have like a set of 3 elements, A, B, and C.
Okay.
They stay in that order. They're non-commutative.
Okay.
So you don't have to worry about like things like B, A, C, or anything like that. They're staying A, B, C. What changes is the order in which you multiply those. And multiply is kind of a general term. It's just you're performing an operation between 2 of those elements, and you can only be performed on 2 at a time. And so one option is that you could first multiply A and B, and then take that quantity and multiply it by C.
Mm-hmm.
And the other option is that you could multiply B and C, and then take that quantity and multiply it by A on the left. Mm-hmm. So that's where you're delineating the parentheses. It's just like an order of operations, basically.
Okay.
And as soon as you add another one, as you add a 4th element, you're going to have 5.
AB.
5 ways.
It's like A, B, B, C, C, D. Right?
Okay.
And then
you jumped up, but yeah.
Okay, so you have a sequence of some, is it would you say it's n numbers or n elements?
So n, this is what I've also found when doing this research, is that depending on what you are using n to denote, it can get a little bit confusing. Mm-hmm. But like, yes, if we're talking about a sequence of n elements, then you're going to have a correspondence with a polygon that has n plus 1 sides.
Got it. Because the number of ways in which you can multiply do the order of operations on a list or string of n elements is related to the number of ways that you can triangulate in n plus 1 n-gon.
Yes, exactly.
And these are both related. I keep on forgetting the name of that sequence.
Yeah, these are both. Both of these are related to the Catalan numbers.
Okay, the Catalan. I'm going to write that down.
Yeah, there are like hundreds of these different interpretations of Catalan numbers. There are hundreds of Catalan objects.
So they show up everywhere.
2 of them. Yeah, they're like very ubiquitous.
Wait, okay, when you say elements, like, so like if we were just talking about numbers and multiplication, then why does it matter the order in which you do these operations?
Why it matters is a question that I don't concern myself with.
All right, we'll get to that later. So, I guess so can you tell us a little bit about where the sequence comes from, or where it shows up?
Yeah, so it shows up in these 2 instances. It also shows up in these things called Deke paths, which are named after a German mathematician. And Deke paths are basically they're these paths that are sequences of vectors 1, 1 that can't cross the x-axis when you go back. They're 1, 1 and 1 negative 1. So you're basically like moving up, and then you could move down and over, but you can't cross the x-axis, and you can move up and over, and you can make these little like strings, these little like zigzags, basically. And I don't know very much about these Deke paths. It's kind of the next stage of where my research is going to go, is looking at these and their connections. But what's like important about like all of the different interpretations is that because they're all related to the same sequence of numbers, there must be some bijection between any 2 of them.
And bijection, do you mean like a relation, or what does that
Yeah,
mean?
so a bijection in particular is basically a mapping from one interpretation to another that has to be both one-to-one and onto, injective and surjective. That's why it's called
Oh, I
bijective.
learned about that. No way.
Yeah, so that comes up, and that is like using something like a bijection can prove things about uniqueness. Um, is one of the things that I've been working on. But like it just means that there are ways to go from something like a string of three elements and a triangulated square that maps one thing to one thing and only that thing.
So this is all like fine and dandy as like theory, but like how does this help us in the real world? I know you were
I
talking
was
about
waiting for
like
Finian to ask this.
today's true pure math is tomorrow's applied math, but at what point are we like with the stuff you're studying? Is it transitioning into applied math? Is it purely like theoretical still? Like I doubt
Hmm.
this stuff is going to be used to like make me a coffee or something like that.
So yeah. See, this is the question that I'm afraid that that I was afraid you were going to ask me, that I knew you were going to ask me, which is that I don't know personally because I am not an applied mathematician. I don't find the application to be the most interesting part of mathematics, but
And
I
that's
do
totally
know that
fair.
there are Catalan numbers are a very old sequence of numbers, and they definitely find themselves in application purposes. Like strictly what I'm looking at is mainly on a curiosity basis. Like it's kind of just like this is an interesting connection, and then you explore it further. And I do have a more specific research question that is specifically related, but is harder to answer. But the like a broader answer that I could probably give you is that um particularly triangulations and these paths are very closely related to algebra and also like things like graph theory. And graph theory is very applicable. Like graph theory is used in so many ways. Um,
Yeah, I've heard you
but
talk about graph theory, and you're like, oh, graph theory it gets used in so many things, but you never tell me. Uh,
well,
like
yes,
what?
this is because I'm a number theorist at heart, and number theorists don't do applied math in a lot of ways,
That's.
unless you're talking about cryptography.
um.
Hmm. Wait, what is graph theory
So
exactly? I should, or well, if you're gonna stay on this, Finian, you can do that.
no, no, no. I was going to ask about graph theory. So
I don't know
Um,
what it is.
what's graph theory?
Cool. So graph theory is basically a graph is just anything with vertices and edges. Um, and draw you can draw edges between your vertices for any given reason. Like for instance, the kind of like classic introduction to graph theory is the Konigsberg Bridge problem. I don't know if any of y'all have heard of,
No.
but
No.
basically there is this theoretical town, which I don't know if it is actually real, but it has like three mainland bodies and like an island, and there are rivers between them and bridges connecting the island and the different like chunks of mainland across these um, different waterways. And the question that was asked is like, can you walk across all of the bridges only one
Uh,
time and like end up on every single piece of land, but only
Mm,
do it once, and also end
mm,
up back where you started? And there are like various questions you can ask about it. And there turns out to be properties about like the degrees of the different vertices, like the parity of of vertices actually is what is relevant. So like if a vertex has an even degree, then you can make these kind of walkways through it, and it's a little bit denser than that. And I haven't taken graph theory in a few semesters, a couple of years at this point, so I am less familiar with it. But like that's kind of the classic problem. But you can have
Interesting.
graphs that basically a graph theory was a way to translate that problem into math in a more digestible way. And so instead of you're talking about like mainland chunk A and island B, you're talking about, and then the bridges between them, you're talking about two vertices on a page and a line between them, and what are the questions you can ask about that, and what are the ways you can connect them. And yeah.
So okay, because I've seen some things online where it's like, oh, here's this interesting shape. Can you like trace it out without like and get back to the same spot without like tracing over your line?
Yeah,
is that sort of the idea? Okay,
that's graph theory.
Why is it useful? Because you said there's some applications. So do you know?
Yeah.
It's those fun little clicker games of going out.
Well, they are very fun.
Not having to cross back over your lines. That's the whole backstory behind graph theory. They just wanted that game.
Well, when you're talking about graph theory and you're talking about questions of like, can you make this trip on a graph without like picking up your pencil, you're talking about optimization. Like, can you go from these points to these points in the most optimal way so you're not retracing your steps? Like, that's a classic application of like any field of math is optimization problems. And also, like, you see optimization problems honestly most frequently in calculus. Differentiation is an optimization problem, but that's also optimization in graph theory.
That's really interesting. I had never thought of like differentiation as optimizing, but it totally makes sense.
Like Finian, when we learned optimization, it was in calculus class, right? And you would like find the derivative, set it equal to 0, and you find like, you can find like the min and max of some function, right? That's like kind of the idea.
Okay.
Yeah.
That kind of optimization.
So you've now been taking math for many, many years.
Yes, well, I'm still an undergrad, so don't give me too much credit.
Still, you've taken math longer than we have because you're a mathematician, and while we may be engineers, we don't do like true math.
Well, this is what's such an interesting conversation because I don't care about the application of any of my work, and all of the math that y'all do is so like application based.
Yeah, it's like entirely application based.
Yeah. But anyways, continue.
What we were thinking about this earlier about like schooling and how math is taught. How is it different? Because you and I are childhood friends. How is it different than like how we were taught math, and what's something that you would like to see in the world of math education?
Well, I mean, I would say that like learning math has as much variability as like kind of any other subject could have. So like, I mean, I've had various professors that teach in different ways, and I mean, I think math definitely lends itself to like a lecture style type of learning.
Really?
Like, yeah, I mean, like it makes sense there, like especially in the more introductory courses, like. Well, the most frequent most recent intro course that I took was modern algebra, and something like that. Algebra is about on an intro level is about group theory, groups and rings and fields, and it's very heavy with definitions. Like that is a very well established field. So when you're learning stuff like when you're learning that, it's very much like what defines a ring, what defines a field. It's memorization. It's I mean, it is difficult, but it is like, it is more like internalizing stuff that has already been established.
Okay.
So this is why like I found the lecture to be like the most useful, but I also have had professors who teach in like kind of like a flip style classroom. So I will watch a video or read a chapter or do some number of problems before class. And then when I get to class, I'm given a set of proofs to try and do, and I work them out with like my peers, and then try to learn in that way. And I think there are pros and cons. I like particularly the professor I'm thinking of. I love him very much, and he's taught me multiple classes at this point. And he always kind of does this different like flipped classroom style. But I also know that a lot of my like fellow math majors really don't like that style of teaching. So some of it is up to preference, but I think there are reasons that both are good.
Wait, do math students read the textbook?
It depends on the math student. I think
this is such a Liam question. I hope you know
Well,
this.
I don't know
This is a
many
very
engineers
Liam
that
question.
like spend their time reading the textbook. I mean, I
Well,
don't know. I feel like it's not necessary.
Like once,
I have
a couple times.
I would say that it's so like person by person. It's one of those like I would think it'd be hard to generalize. It also depends on the class. Like
that's a perfect answer for Liam. That's just what he was wanting to hear.
I think there are definitely courses I've taken where like reading the textbook is like I haven't cracked the textbook once unless I'm looking for like the homework problems. And then there are courses where it's like
Well,
yeah. All right. It's like I don't
that's why you buy the
understand.
textbooks.
Yeah, no, pretty much. But some of the courses it can be helpful to either try and read a chunk of the relevant chapter beforehand to like just like have the material at least kind of familiar before I go into class, or then go and read the chapter like after class to try and make sense of it if like whatever it was taught that was like very dense or hard to follow. But I will say that reading like just trying to read a math textbook is it's so hard to learn from just a textbook when it comes to
Well, they all
math.
try to sound so fancy, I feel like.
Yeah.
It's like get over yourself. Like it's just speak normally.
It's all of formalization. There's a very specific way to write mathematical statements.
For math, like when you're like learning it, is it better for the kind of math that you're doing, like to visualize it, to give these like visual examples? Is that even possible? Because you're talking about graphs and like chords through polygons, but is it easier to show someone stuff like that in a classroom setting and more like valuable for them as a student? Or is it better to give them the formal definition of like what you're doing? Because you mentioned chords, and all of us might know what that is, but people at home might not understand what a chord is in terms of like math. Chord is.
So I mean, well, it's so just like very briefly, a chord is going to be like basically a line segment that connects two vertices, and like it's kind of like if you think about like a chord in a circle, it's just like going to slice off like a little like kind of arc of that circle.
In that case, it's not a vertice though, right? Because
correct.
Well,
yeah,
it's
the same terminology.
It's like bounded by the shape.
Yeah, okay. But that's kind of what I'm trying to get at, is that like a chord is an internal edge.
So like the diameter is a chord that goes through the midpoint of a circle.
Yeah.
Got it.
But if I'm thinking about Finn's question, I mean I don't think that there is. I don't think that you can do one without the other. Like,
okay,
I don't think that I would be able to really like understand any of the math that I've learned without doing examples. And that's honestly one of my critiques of like a flipped style classroom of learning, is that like it does tend to throw you into the more abstract end before getting your feet wet in examples. So like just like for instance, when I was taking real analysis, like you do a lot of what are called epsilon delta style proofs, and these are epsilon and delta represent like little tiny movements left and right or up and down, just like infinitesimal differences that you're minimizing. And like proving that something is the derivative of something else involves one of these epsilon delta arguments. And there's a lot of like theory that then you can go into once you kind of know the structure of an epsilon delta proof. Like you can prove things about I don't know, just like different, like if you have like an equation of the form like y equals x to the n, you can prove like the derivative formula once you know this like epsilon delta style proof. But like what's helpful is actually doing one where it's like, okay, you have y equals x cubed, and then the derivative would be like 3x squared, and then you use an epsilon delta argument to prove that rather than jumping straight into the abstract where it's like you have an exponential, or not necessarily, that's not an exponential, but you have like a polynomial and you're looking for what the form of the derivative would be. I think the concrete example I need before I can do something like
Right.
a general proof.
But whoever invents that doesn't have a concrete example, or do they? Like,
Oh, I think they definitely do. That's kind of what I was saying
that's like
earlier.
how
Like,
they reverse
yeah,
engineer it, I guess.
a little. I think there is a lot of reverse engineering that happens in the preliminary stages of math research. Like, because what I'm doing right now is I like what I did today was I drew like every single one of the 42 different ways to triangulate a heptagon, and I was thinking about like basically there's these things called dihedral groups, which represent the different ways to permute polygons that preserve the structure of the shape. And I was like, okay, what if I apply a rotation to a particular triangulation and then like a flip? And that's a whole other, that's like a very, that's group theory. That's just abstract algebra. But I was drawing all of these shapes just like on a piece of paper, and I spent like an hour and a half doing that. Like I feel like I feel like there's like I have like an inkling that's like, okay, if I use the dihedral group, maybe I'll learn something about like which triangulations share a chord, because that does, there is my broader research question, which I haven't actually talked about, but like is about shared chords in these different triangulations. And it's kind of just about like following instinct, making a bunch of pictures, and then being like, what are like, where is the pattern here?
Interesting. So now that we have
can
a
I for a second
little, no,
we
go,
got a
Liam.
delay there. I was just gonna zoom out for a second and ask, if I were to hear someone's doing math research and they're actually on a whiteboard actually testing things out and trying to prove something, or they have a thesis, I would think it'd be like graduate work. I mean, how many undergraduates get to do this kind of stuff? Would you say is this typical? Or are you pretty smart? Is this
Toot your own horn, Theo. Toot your own horn.
exactly.
I would say that it definitely depends on the institution, and Swarthmore is a very small liberal arts college. So
Mm.
I like, and one of the benefits of that is that I think that I get to have a more personal connection with a lot of my professors. Like there's
Mm.
no graduate students, so I'm not taught by any TAs. I'm only taught directly by my professors. And along with that is kind of the opportunity to work with them directly in these summer programs that are, I mean, I had to apply, but it's not, and it is competitive, but because the school is so small, the math department is also quite
Yeah.
small. So it's kind of it's on the basis of this is what I had interest in. And so I just had to speak to my professors and like learn who was going to be hiring students for the summer. What are extraordinarily competitive, and which I did apply and did not get into a single one, are REUs, which are like research experience for undergrads, which are these more like nationally funded research experiences with these like that are hosted by different institutions and hosted by different professors, but are like getting applicants from like all across the country, and also only have enough money to fund like 6 to 10 undergrads.
Yeah.
And those have like less than 1% acceptance rate. Like they're getting like hundreds of applications. That is like crazy. Like I think I know a couple people who have been able to like get into those programs. I was not, but those are a little bit out there
Mm-hmm.
and
To
more
like
intense.
sit there and say that you know a couple of people that have gotten into these programs
Yeah.
after just saying that it's like 6 people out of like multiple hundred is pretty crazy. You
It's-
gotta admit.
Yeah, I mean, some of the people that I work with and take classes with are on another level.
And so this
So
research you're doing, is this something
yeah.
you got to, is this something in particular they were interested in? And, or is there a paper being written? I guess I don't really know how research works, but where does what you're doing, what does it funnel into? And who's
Mhm.
trying to get
benefiting
this
from
research
it.
done.
Yeah.
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 So
Why
I'm
does it matter?
working. I I am working currently under one of a visiting professor at Swarthmore. His name is Pat Devlin. He's a great guy.
Name drop.
And yeah, but that's my boss. Love him. And he is generally interested in things of like the discrete flavor, like I said earlier. And he's kind of just like I didn't even know what I was working on until I got there on the first day, and he like pitched a bunch of problems and was like, I just find these all interesting and you can kind of do whichever one you want. Um, and this is why like working at like my home institution is a little bit of like it's baby steps in research. It's like meant to be a research experience for undergraduates who haven't done research before. It's almost more about like getting the experience of of learning what it means to do math research and kind of how that looks, less so about like generating like tangible results or like making a publication or something by the end of the summer.
Got
Which
it.
yeah, which I do think makes sense for like the undergraduate level.
Pretty cool you get
Like
that
if you,
experience as an undergrad. That's
Yeah,
yeah,
it's definitely
that's
if
probably
unique and
amazing.
and
Great
grateful.
for the
Yeah.
resume.
if
Yeah,
if you
for
were
sure.
All about the resume.
if you were to write a publication, how long are these? Because like you go onto like the library website and you look up a study and it's like 200 pages long. I doubt you're going to be writing something that long. Is it going to be like
Definitely not.
40,
It
20,
really depends, and
5?
Stop saying
what's
numbers. He's gonna.
yeah. Come
No,
on,
I know, I know,
man.
I know.
I would say that what so
2.
kind of what the hardest thing about writing a proof, um, or I guess maybe like a better way to put it is that like short proofs are sometimes better proofs. Like the shorter your paper, honestly, oftentimes the more like renowned it will be because that means that you've found a very like elegant way to go from point A to point B. Um, Particular what comes to mind, um, I just took a class on this. Like there is a proof that is it's not a long proof. I haven't read the whole paper myself because it's so dense, but it's not very long. In I believe it was 2016, this Ukrainian mathematician, Marina Vyazovska, proved the optimality of the E8 lattice packing, which is it's entirely different field. It's analytic number theory, very different field of mathematics, but she proved the like optimality of this lattice in a like this elegant merging of modular forms, Fourier series, and lattice work. And
My favorite work.
like this is like one of those things that like an example of something that I was saying earlier where it's like and she won a Fields Medal for this, which it was like it's groundbreaking math, and it's because she merged these three fields in such an elegant way. And so like something like the length of whatever work I would produce, it's variable because there are proofs that are like hundreds of pages long that are equally as impressive that require that like level of density in order to get from point A to point B. Like there are now, because of computers, there are guess and check proofs. There are proofs that like their strategies to go through and like check all of the cases one by one.
Right.
But something like what Vyazovska was able to do was produce like such an elegant transition from this question about lattice density and optimization and producing the result in like just those short pages is like that's high level math.
So it's about, like finding, like you said, finding connections between different fields to, like, I guess, like finding relationships between things. And then eventually that can help you do a new set of problems. But like your specific focus is finding, I guess, patterns and less so like caring about what those patterns help you do.
Yeah, I think that there is a relationship, I think, between pure mathematicians and applied mathematicians in that the theory behind what allows applied math to happen comes from pure
Right.
mathematicians.
You are like
Like,
they are they're standing on the shoulders of giants, and the giants are you.
yeah, exactly.
So wait,
Wow.
so can you just I guess restate what you just mentioned your question earlier, your research question. Can you restate
Mhm.
what that was again?
Yeah, so I actually didn't, I don't think I ever said it because I was
I
trying
don't
to
think you
like
did.
Finney probably
give
cut you off or something.
Yeah, probably knowing me.
um but so what I am trying to figure out, and this is like the part of the research that definitely does not have an answer yet. A lot of like things like Catalan numbers and bijections, like there is a lot of work that's already been done on that, but this question doesn't have an answer yet. And it's basically given given about like a set of triangulations of an n-gon of any magnitude,
Mhm.
let's require that this set, any two that you choose must share an edge. It doesn't have to be the same one, but like if you have like I don't know, like 12 of them, and you pick the first one and the ninth one, they have to have just one at least chord in common. And then you could pick a different
Okay.
set of two, and those two have to have a chord in common. It doesn't have to be the same one. It could be, but it doesn't need to be. But the question is basically what is the upper bound of the size, like the cardinality of that set? Like how big, how many can you have that share this property? And I mean that's so like all of this work on like finding bijections and understanding like the patterns and like the properties of these triangulations and how these relate to Catalan numbers is like in an effort to try and make a statement about how big you can make that set.
Okay. So just to clarify, you have some n-gon, two-dimensional n-gon, right?
Yeah.
Um, and then you draw a bunch of chords that can't cross. Like you connect a bunch of vertices, draw a bunch of chord. Do they um do these all have to end up being triangles basically?
Yes.
And then is the triangulation the set of all the triangles or the number of all the triangles? Like what is the
So
triangulation?
the triangulation is just so like say you have like a pentagon and you connect like the bottom vertex, the bottom right with the top one and the bottom left with the top one. That's a triangulation. That
Okay.
it's those like two
With
chords.
three triangles, right?
Yes.
Okay.
And so and the set of all possible triangulations of a pentagon, there's only 5 of them in total at all.
Right.
And those actually all of them, if you consider like all of them, any two can actually that's not true. But you can generate all of them from one. But that's a different question. But like the maximum number of different triangulations in a possible set, for instance, like for a pentagon, let's say you want to have um like if you consider just that chord, the first chord, like the one from like the bottom left up to
Yeah.
the top, there's
Mhm.
two triangulations that share that chord because you can draw the other line from the top to the other
Oh.
bottom one, or there's or you can draw the other chord. You see, like
Okay,
I think a visual would help, but like
so there's five different ways you can triangulate a pentagon, right?
yeah,
And like with like considering those five, there are some of those share common chords.
yeah,
So keep going with what you were saying. So what's
yeah.
the
So the question is like, how many can you put together such that any two of them share a common chord? So like,
any two triangulations
yes, any two triangulations share a
share
common
at
chord.
least one common chord?
Yes. So like, for instance, you can create a
Oh.
set of two of those pentagonal triangulations where two of them share the same chord, and but you can also like if you go up a dimension, like if you are talking about a hexagon, you can create at least a set of 5 elements that like that share a common chord. And the reason for that is because of the recursive nature of the Catalan numbers. Because if you think about starting with one chord, then you've then you're just considering now a pentagon because you've basically lopped off one of the vertices. And we
Okay.
already know there's 5 ways to triangulate a pentagon. So now you have automatically 5 triangulations of a hexagon that necessarily share the same chord. But that's also subtly
Oh.
subtly that is a different question though, because
Yeah.
the question doesn't require that that chord be the same. So it's what I'm trying to like think about currently is whether or not requiring that that chord be the same actually gets you more in that set than if you like want there to be variation. Because I don't know, and this is because of like I haven't answered this question, so I don't know. But
It's what
once
you're
you
working on.
yeah, and once you go up a dimension again, it gets even higher. Like if you're considering like a heptagon and you like require that they all of your triangulations share the same edge, now you can be certain that your set will have at least 14, in fact only 14 of triangulations because now you're considering a hexagon because you already know that one of those vertices has that edge right in front of it, and so you lop it off and now you're considering just the hexagon. Um and 14 seems to be in the very, very preliminary work that I've done on this, like kind of the largest set that I can make. So I don't know. But
And
yeah,
so
that's the
the
question.
goal is to sit like just to make sure I understand this. You want to find what is the maximum number of triangulations such that any two will share at least one common chord.
Yes.
Yeah.
Okay.
Can I
Like
can I
given
just
an
sorry I
n-gon or like because that's going to depend on like are you saying like given a specific shape? Like you
Yes.
okay.
So like
Sorry.
you're given an n-gon. The You're only going to consider triangulations of the that n-gon,
Okay.
but the goal is to generalize over
As a
n. So
function of
like
n.
yeah, as a function of some type of relation to yes.
Okay.
So because when you're working in low enough numbers, like working with like a pentagon or hexagon, in theory, I could probably try to like look at all of them and just like pick out whatever the largest that I possibly could. But as soon as you even move up to 7, like 42 is already a lot to handle.
Yeah.
So
yeah.
the generalization is the goal. Yeah.
Liam, what were you
So
saying?
you,
Can I just
yeah, Liam.
clarify something real quick or not re-clarify, I just ask is the triangulation, is that where you're connecting all the vertices through it? Like in a pentagon, I could make a W in it basically. Is that a triangulation, or a triangulation is just any single triangle that's made in it? I guess I missed
The
that.
triangulation basically there. So a general triangulation will have n minus 3 chords in it, like necessarily. Um, you have
Okay.
to divide the shape into only triangles. Like you couldn't have just one chord in a pentagon and then leave the other 3 vertices untouched. Like you have to, or I guess the other two, you have to have a full triangulation for it to count.
And a
And so I
triangulation
just
is
think about
whenever
it.
you make a shape fully out of triangles.
Mhm.
Okay.
Wait, no, I just meant with the W. Like if I think about a pentagon, if you have one of the points on the top going down, if you make a W-ish shape, that'll split it into triangles. Are the 5 just that and then rotated 5 times? Is that what the 5
No,
are for a pentagon? No, is that
no,
am I
because
misunderstanding what you mean by that?
the pentagon will only have 2 internal chords in its triangulation because your n in that case is 5 if we're talking about n as the number of vertices. So if you think about there is like a W style triangulation, but that includes 2 external edges. If you're like trying to make that W, you don't really consider the external edges of the pentagon. You're only really thinking about the 2 in the middle, and those two you could have one that goes like horizontally across the pentagon, and then another one that comes from one of those vertices and then goes to one of the ones in the bottom corner. And that would be, yeah, a rotation. But then when you move up a dimension, there are there are families of these triangulations that can't be translated into one another. So, and that's kind of related to what I mentioned very briefly about with dihedral groups, which is all about rotations and like rotations and reflections, basically. But like, so if you think about like, say, like a hexagon, kind of one of like the first triangulations you could think of is if you have like one vertex, and then like you have three chords coming out of it, and it goes to like the three opposite vertices, and it makes a little like fan. As soon as you change one of those so that it's not so not all of them are like starting from that same corner vertex, there's no possible way to rotate or flip your starting triangulation into the other one because you've moved the orientation of that chord. But there is a set of 6 where if you do rotate, you will create different triangulations that are like in that basically like rotational family, kind of is what I was actually working on this afternoon.
And can I just ask again, what did you mean external vertice when you said the pentagon? Like it has 5 vertices. How are they
Yeah, so
external or
external
not?
edges, like the external edges are like the ones that are like actually making the shape of the pentagon, and then the internal
Mm-hmm.
ones are the chords that will the
Oh, when
like
two chords make it. Okay.
yeah,
Interesting. Okay.
because there are like there's a
Yeah.
lot of math you can do about like the number of chords in something like a connected graph, and that includes those external chords. But the triangulation is really only dependent on the internal chords rather than those external ones. And the degree of the vertices, um, which is the way to kind of the key to translating that bijection between parenthesis strings and triangulations is like vertex degree, which is like the number of edges coming out of it. That also only is concerned with the internal edges when you're talking about triangulations.
Okay,
Just
so
dense.
just
Yeah.
all of us just like stopped talking. It was like we're all trying
we're
to figure out
processing, yeah.
what
This
you're
is like
talking
it would
about.
be, I promise you, like, and this is also kind of related to like the question of like mathematical education. The visual is so helpful.
Super
Like
important.
That's why Finian's
I
gonna be doing some animations for this.
Uh,
So I want to hear about. Obviously, you haven't solved this yet, but like sort of the plan of attack, because sort of what it
Mhm.
sounds like is like, okay, you say for n equals 5, here's what it would be. For n equals 6, here's what it would be. And you sort of, my guess is you'd sort of try to find some sort of pattern and then generalize. So is it
Yeah.
sort of like a do it, see what that gets you, do it, see what that gets you, and then you're trying to figure out the pattern? Or is there like a better, more analytical way to approach it?
So I think that like strategies like that are definitely still something that I'm learning because this is my first like real research experience. But um thinking about basically right now it's like, okay, I'm considering the relationship between these sets of parentheses and these triangulations towards the end of trying to answer a question about chords. So the process has been like, okay, well now I understand they both are connected by these things called catalan numbers. And so I did a lot of work on like, so what are these numbers? What is the recursive relationship between them? There's something called a generating function, which helps you solve that recurrence, and create a general formula, um, which I looked at briefly and will probably return to. And then I started moving into like, okay, so I'm trying to figure out basically things related to Catalan numbers and something like triangulations and something like parenthesis strings. Like there are different interpretations of the same set of objects, but you could do different math on them. So like a triangulation is like geometric and you can do geometric things with it. But a string of parentheses, that's algebra. Like that's
Right.
associativity.
okay.
So it's like, can you answer the question in a different way using a different field? And like one of those ways might be a little bit easier or a little bit more straightforward. Or like maybe I have like a personal like set of knowledge that's like more related to algebra than something like geometry. So like making those translations is why that's why like I'm doing that. But so then I was like, okay, I'm trying to answer questions about like which of these triangulations share a chord. Let me figure out like how I can tell if like a particular string of parentheses that corresponds to one and only one triangulation. If like you give me two of them and I don't have their triangulations, how could I tell from just the parenthesis strings whether or not they share a chord? And there's like I like kind of developed a method to do that, which is translating the parentheses into a degree sequence of vertices, and then there are certain properties of that degree sequence which can tell you whether or not it will, when you draw that picture, that you will have one of those chords in common.
And so is a big part of this process learning about all the other research that's happened on the subject? Like I'd imagine that's really
definitely
helpful.
Yeah, it is super helpful, and it's kind of a double-edged sword because, so for instance, like one of the things that I kind of came across when I was like looking at, basically I had like the set of 14 for a hexagon, 14 triangulations, and I was like, okay, I'm gonna draw a graph where all of the vertices are the different, like they represent different triangulations, and I'll draw an edge between two vertices if they share all but one edge. So if they're similar in every way except for one chord. And what that generates when you look at it in an n+2 dimensional space is something called an associahedron, which I had no idea was a thing. And it's like this really cool like polyhedron, three-dimensional object, three dimension only specifically in that case. But like that, and then I was like, okay, I've made this picture, and I was like, whoa, this like it's basically it's a shape that has three square faces and six pentagonal faces, and it's made by like every edge that connects a vertex and that picture means that you've performed one application of the associativity rule on your string of parentheses to go between the edges. And then I was like looking it up, and like it's called that because some guy already did all the research about that and like has learned about that particular structural polyhedron and like has published things about it. And so it's like it's both like that's a good sign. It's like, okay, I'm moving in the right direction. Like somebody else found this interesting and I should probably read about that if I want to go down that path. But also then it's like, okay, like someone already did the work here. Like I don't need to
What's the
do it on my
point?
own
Yeah.
again. Yeah.
Oh, was this the stuff you were talking to me like yesterday about?
Was I?
We were talking to the car or something, and you were like, "Yeah, I found out this thing," and then I Googled it, and someone had already like researched it. So I'm like, "What's the point of me researching this if someone's already done it?"
No, yeah, pretty much. It's like because there are so many of these different Catalan objects, there's so many rabbit holes to go down. Like, and this is true for a lot of math research, but like particularly with this problem, there's just like so many different directions that you could theoretically go down. And it's like, okay, I stumbled upon something that was really cool, but it's like already been like that path already had someone already went down that way. So like
Right.
I could go and
Okay.
research it if I was like personally curious about it, and maybe it will help in trying to answer like my own question. But doing more work on like the geometry of that polyhedron, not really worth my time. Somebody else already did it.
But it's pretty cool. So what you're doing specifically, no one else has come up with a solution for.
Not this question, correct? Yeah.
It's pretty cool.
Listeners,
It's
feel
pretty
free
cool.
to give it a shot.
Which means
Yeah.
maybe I will not find an answer. Is the other the other thing?
Maybe you will. Maybe you will.
Who's
I'm-
to say?
It'd be
I'm
pretty cool, though.
curious, like,
Yeah.
because like, okay, my first thought of like how you would solve this, if like you presented this problem to me, I would figure out a way to like make a computer program that could simulate this, or could sort of like take some n-gon and like
Yeah.
try to figure out the different connections and how many triangulations and like do that, and then I would like have it run for 1,000 and like, so okay, I'm gonna say it first, and then I think there might be a reason why this isn't a thing, but maybe you try with like 1,000 n-gons, and then you can sort of like graph the data and see if there's some sort of like function or curve fit that could like describe the relationship between all these points. Have you thought about, is that just like way too computationally expensive, or like have you thought about that? Or
So programming for this problem definitely would be useful. I don't have a ton of experience in it, but I like know a little bit. But like generating, particularly when generating images of like all the different triangulations, when you get to like a really high number, and generating like something like these graphs that like revealed the associahedron, definitely would even like require the use of a program to generate that for higher Catalan numbers.
Right.
However, the explanation of why is not going to be able to, you can't, like, your program will not be able to tell you that. Like, why, like,
It'll just spit out the answer. It won't be
it'll
like
give you
this
data.
is the
Well, right. And then I feel like the next step would be then
well,
yeah.
the research he's doing is all about figuring out what the association is so that he can program it and be like, oh, I want a 32-sided like triangulation. What is the da-da-da-da-da-da? So
Yeah.
I don't remember all the terms that you used, so I filled in does.
That could be, I guess, the end result.
Do you know any Python or any programming that could help with this? Like, I imagine it could be really useful.
I do. I know Python, and I can program a little bit in C, and that there's also definitely like particular like math software that is better for generating these images or generating this data. But I don't have that like particular skill set, so I'm working the old-fashioned way, I guess you could say.
Yeah. Well, it sounds like you're doing a lot of, frankly, groundbreaking work.
Sure. Let's call it that.
Trying to answer a question that no one before has answered. Yeah. We're right at the end of our time. I would like to formally thank you for coming on the podcast and sharing your insights into the world of math.
We definitely,
there's a lot more in math than I expected.
I think the three of us combined still don't understand it half as well as you do, but like,
oh, absolutely,
no, it's very cool to hear.
We need to do some research.
Yeah,
and
then we'll do research. We'll find out that's already been solved, and we won't tell you.
Yeah, no,
you just feel bad.
My research experience. No, I appreciate you. It's definitely difficult to try to explain. So, I know it's a little bit dense, but I appreciate y'all letting me try to unpack it a little bit with y'all.
Maybe next time bring a whiteboard.
Yeah, that could
next
be
time next time he'll give us a solution.
Exactly.
Yeah,
on a whiteboard.
No, when I definitely finally publish a paper at the end of the summer, because that's for sure going to happen.
Yeah.
Right. I'll forward it to you all for sure.
Sick.
Oh, thank you.
All right.
Wonderful.
Thanks so
I'm
much,
looking forward to it.
Thanks, guys.
Well, have a good night, Theo.
Bye.
Take care.
You
Thank
too.
you.